In this lecture video, we're going to be looking at example 5.3, which involves a 2x2 complete factorial treatment structure. Let's look at a description and an overview of the context of the example. Consider a 2x2 complete factorial treatment structure. The two fixed effect factors under consideration will be denoted by factors A and B. This 2x2 complete factorial treatment structure consists of 2 times 2, or 4, treatment combinations, which are denoted by A1B1, A1B2, A2B1, and A2B2. Now note that every level of each factor occurs in combination with every level of the other factor, and so this is indeed a complete factorial treatment structure. The 4 treatment combination means, the μij's, are given in the two-way table on the following slide. And so here we have the two-way table, and we see that the mean of the treatment combination A1B1, which is denoted by μ11, is equal to 60. The mean of the treatment combination A1B2, denoted by μ12, is equal to 100. The mean of the treatment combination A2B1, denoted by μ21, is equal to 80. And finally, the mean of the treatment combination A2B2, denoted by μ22, is equal to 120. Now recall that in the means model representation, if the treatment means, the μij's, are fixed effects, then the μij's are constants with arithmetic mean equal to mu, and we see the calculation that we're talking about here. And if we want to emphasize or reiterate this particular calculation in the notation for the arithmetic mean, then we can denote it by mu bar dot dot, as we have on the right-hand side. Now recall also that in the effects model representation, if the treatment effects, the alpha sub i's, the beta sub j's, and the alpha beta ij's, are fixed effects, then the following constraints hold among the various parameters. So the alphas sum to 0, that is, alpha 1 plus alpha 2 is equal to 0. The betas sum to 0, so beta 1 plus beta 2 is equal to 0. The alpha beta ij's are such that if we sum along either of the two indices, we get 0. So if we sum the alpha beta ij's along the first index, along the I index, then that sum is going to be equal to 0. And likewise, if we sum the alpha beta ij's along the second index, the j index, that sum will also be equal to 0. And those two facts imply that if we sum all of the alpha beta ij's together, we would again get 0. Now let's look at the values of the effects model parameters. The two-way table did not give the values for these effects. The two-way table gave the values for the individual treatment means, but using the given treatment combination means, as well as the constraints among the effects model parameters, it can be shown that the parameters for the effects model representation of the model are as given here. So mu, the arithmetic mean of the 4 treatment means, is equal to 90. Alpha 1 is equal to negative 10, and alpha 2 is equal to positive 10. Beta 1 is equal to negative 20, and so beta 2 is equal to negative 20. And then all of the alpha beta ij's turn out to be 0. So make sure that you can derive these values for the effects model parameters given a set of treatment combination means. All right, let's move on to the next task of calculating the various means and effects associated with this 2x2 complete factorial treatment structure. And we will start off by calculating various means. And so we're going to calculate the arithmetic means for each factor level and also the overall mean of treatment combination means. We've actually already done that last one because we just talked about it, but we'll do it again. We'll show the calculation on the next couple slides. But first, we're going to calculate the row means, in other words, the means of the levels of factor A. And so mu bar 1 dot, that is the arithmetic mean of the treatment means for those treatment combinations that have the first level of factor A. So the arithmetic mean of mu 1, 1 and mu 1, 2. And if we think in terms of the two-way table, that is the arithmetic mean of the treatment means in the first row of that table. That row mean is equal to 80, and so the mean of the first level of factor A is equal to 80. Mu bar 2 dot is the arithmetic mean of the treatment means for those treatment combinations that have the second level of factor A, and so that's going to be the mean of the values in the second row of our two-way table, and that turns out to be 100. And so here we see the calculations in the context of the two-way table, and you can see that I've augmented the table with a column out here to the right to contain those row means. And so the arithmetic mean of the first level of factor A is 80, and the arithmetic mean of the second level of factor A is 100. Then we'll calculate the column means. These are the arithmetic means for the levels of factor B. And so mu bar dot 1 is the arithmetic mean of the treatment means for those treatment combinations that have the first level of factor B. So it's the arithmetic mean of mu 1, 1 and mu 2, 1, and that turns out to be 70. Mu bar dot 2 is the arithmetic mean of those treatment means for the treatment combinations that have the second level of factor B. And so it's the arithmetic mean of mu 1, 2 and mu 2, 2. And that turns out to be 110. All right, so here we see the calculations done in the context of the table, and I've augmented the table with a row for the column means. And so the arithmetic mean for the treatment means in the treatment combination means in the first column is 70, the average of 60 and 80. And then the arithmetic mean of the treatment means for the second column is 110. It's the arithmetic mean of 100 and 120. And then finally, we can calculate the overall arithmetic mean of the treatment means. And again, we can calculate that three different ways. We can calculate it as the, let me see here, as the arithmetic mean of the column means. We can calculate it as the arithmetic mean of the row means. And we can calculate it as the arithmetic mean of the individual treatment combination means. And any of these approaches will give the same value. And we see here that mu is equal to 90. And again, we can also denote this as mu bar dot dot if we want to emphasize the fact that it's the arithmetic mean of the treatment combination means. And so we can demonstrate each of these three calculations by looking at the table. And so here, the cell in the bottom right corner, that is the overall treatment combination or the arithmetic mean of the treatment combinations, and we can calculate that as shown here as the arithmetic mean of the column means. We can also calculate it as the arithmetic mean of the row means, and then finally we can calculate it as the arithmetic mean of the individual treatment combination means. All right, now that we have those, we can move on to calculate the various kinds of effects. Recall that in the context of a 2x2 complete factorial treatment structure, there are three types of effects. Simple effects, of which there are four, main effects, of which there are two, because there are two factors, and then one interaction effect. And you'll recall that we can think of the interaction between these two factors in two different ways, from two different perspectives. We can think of the interaction of factor A with B, or we can think of the interaction of B with factor B with A. But as we've seen in the past, those are equivalent interactions. They're going to be numerically equal, so we just say that there is one interaction effect. So let's calculate the simple effects. So again, the simple effect of a factor is defined to be the difference between treatment means for two levels of the factor at a given level of the other factor. In the notation of the means model, the simple effects are calculated as shown below. So we'll first calculate the simple effect of A at the first level of B. That is given by mu21 minus mu11, which is 80 minus 60, or 20. This is shown in the context of the table, as shown here. So we're calculating the difference in the treatment means in that first column. 80 minus 60 gives 20, and so that 20 is the simple effect of A at the first level of factor B. The simple effect of A at the second level of factor B is defined to be mu22 minus mu12. That is 120 minus 100, or 20. And so here we see in the context of the table this calculation demonstrated. To get the simple effect of A at the second level of B, we're going to take the difference between 120 and 100, and that gives us 20. Next, to find the simple effect of B at the first level of A, that is defined to be mu12 minus mu11. That turns out to be 100 minus 60, or 40. In the context of the table, this is what we're doing. We're finding the simple effect of B at the first level of A, at level A1, and so that's going to be the difference between 100 and 60. And then finally, the simple effect of B at the second level of A, that's defined to be mu22 minus mu21, 120 minus 80, which is 40. And again, we can look at this in the context of the two-way table. We're calculating the simple effect of B at the second level of A, and so that's going to be the difference between 120 and 80. Now, in the notation of the effects model, the simple effects can be calculated as shown on this slide. And so, for example, the simple effect of A at the first level of B is going to be, it turns out that it's equal to alpha 2 minus alpha 1 plus alpha beta 2,1 minus alpha beta 1,1. And so this turns out to be 10 minus a negative 10 plus 0 minus 0. I see I've got a little typo there. I don't have the plus 0 minus 0. Remember, all those alpha betas are 0 in this particular example. And so that turns out to be 20. So the simple effect of A at the first level of B using this formula is 20. The simple effect of A at the second level of B is alpha 2 minus alpha 1 plus alpha beta 2,2 minus alpha beta 1,2. And so that's going to be equal to 10 minus, that should be a negative 10, plus 0 minus 0, or 20. The simple effect of B at the first level of A is given by beta 2 minus beta 1 plus alpha beta 1,2 minus alpha beta 1,1. That's equal to 20 minus a negative 20 plus 0 minus 0, or 40. And then finally, the simple effect of B at the second level of A is beta 2 minus beta 1 plus alpha beta 22 minus alpha beta 21. That's equal to 20 minus a negative 20 plus 0 minus 0, which again is 40. And so we see that the both simple effects of A are 20, both simple effects of B are 40, and that's what we found in our previous calculations, and so that matches up. All right, now that we have the simple effects, we can calculate the main effects. Recall that the main effect of a factor can be defined and computed in two different ways. The main effect can be defined as the arithmetic average of the simple effects of the factor. It can also be defined and calculated as the difference between the means of the two levels for that factor. In the notation of the means model, the main effects calculations are represented as follows, and for each of these two expressions or equations, the main effect of A and the main effect of B, in both of those, I have two representations. The representation on the left-hand side of the equal sign is the representation of the main effect as the arithmetic average of the simple effects for that factor, and the expression on the right-hand side is the representation that is the difference between the means of the two levels for that factor. And so let's calculate the main effect of factor A. And so we'll use the first expression, the arithmetic average of the simple effects of factor A. So the simple effect of factor A at the first level of B is mu21 minus mu11. The simple effect of factor A at the second level of B is mu22 minus mu12. Those simple effects were found to be 20 and 20 respectively, and so the average value is 20, obviously. And here we see how we calculate this quantity in the context of the table. So we want to calculate the mean of the simple effects of A, and so we're going to put that value in the cell that is the intersection of the column for the mean and the row for the simple effects of A, and we'll carry out that calculation. 20 plus 20 over 2, that gives us 20, and so we see that the main effect of A is, according to this calculation, equal to 20. Next, we will calculate the main effect of A as the difference between the means of the two levels of factor A. So that's given by mu bar 2 dot minus mu bar 1 dot. And so we calculated those, and they were found to be 180 respectively. And so the difference is 20. In the context of the table, this is how we're going to do the calculation and where we're going to put the result. We will put the result in that last row. And so, and the way we get it is we're going to take the difference between the means of the levels of factor A. So 100 minus 80, and that gives us 20. And so we see here that we get 20 using both calculations. Next, let's calculate the main effect of B first as the arithmetic average of the simple effects of factor B. Those two simple effects were found to be 40 and 40, and so their average value is going to be 40. And we're going to put the value for the main effect of B using this calculation in the cell that corresponds to the intersection of the mean row and the column for the simple effects of B. And that tells us how to do the calculation. And so we're going to average 40 and 40, and obviously we get 40. So that is the main effect of B according to this calculation. And then we'll also calculate it as the difference between the means of the two levels of factor B. So mu bar dot 2 minus mu bar dot 1, 110 minus 70 or 40. And we're going to put the result in that far right column, and we're going to take the difference between the mean of B2 and the mean of B1, in the table, so 110 minus 70, and so we get 40. And so again, we see that both methods of calculation for the main effective B give us the same value as they ought to. And one reason for having that duplication in the table is to give ourselves a nice quality control check. If we see a difference, we know that we've done something wrong. So we're batting 1,000 right now. We haven't goofed up yet. All right, now we also have the values for the effects model parameters, and so in the notation of the effects model, the main effects can be calculated using the formulas given below. And so the main effective A is given by alpha 2 minus alpha 1, so 10 minus a negative 10, which is 20. And the main effective B is given by beta 2 minus beta 1, so 20 minus a negative 20, and that gives us 40. And so the main effective A is 20, according to this formula, and the main effective B is 40, according to this formula. And we see that that matches up with the calculations that we did previously. So we really have three different ways of calculating the main effective A, and three different ways of calculating the main effective B. They're all algebraically equivalent. It's just which one we use depends on the information we have and which one's more convenient. And if we're doing this in the context of the table, we will probably go ahead and calculate it two ways, just as a nice quality control check. Okay, next let's calculate the interaction effects, and the location in the table that we're going to put this will be at the bottom right hand corner, and we're going to calculate it two different ways. The interaction effect can be thought of this way. The interaction of one factor with another can be computed as the difference between the simple effects of the first factor at each of the two levels of the other factor. We can think of the interaction of A with B, and so by definition that would be the difference between the simple effects of A. The simple effect of A at the first level of B is mu21 minus mu11. The simple effect of A at the second level of B is mu22 minus mu12. We could also, well, let me see here, so let's actually do that. So the simple effects were both found to be 20, and so the difference between them is obviously going to be 0. And so what that tells us is that the interaction of A with B is equal to 0. And we can demonstrate that calculation by taking the difference. We're highlighting what we're going to take the difference of, 20 minus 20, and so we get 0. Next, let's think about the interaction of B with A, and so by definition that would be the difference between the simple effects of B. The simple effect of B at the first level of A is mu12 minus mu11. The simple effect of B at the second level of A is mu22 minus mu21. Both of those simple effects were found to be 40, and so obviously their difference is going to be 0. And so the interaction of B with A is 0. This shows the calculation in the context of the table. So to find the interaction of B with A, we're going to take the difference between the simple effects of B, and so 40 minus 40. And in particular, we're taking the difference between the simple effect of B at the first level of A minus the simple effect of B at the second level of A. And so we get 40 minus 40, or 0. And as we've discussed before, the interaction of A with B is algebraically equivalent to the interaction of B with A. And you can look at those expressions on the left-hand side of the equations in both those equations, and you can see that they're just written in different order. So they're algebraically equivalent, so they're going to be numerically equal as well. And so based on that, we see that those two interactions are the same, they're equivalent. And so we don't need to talk about two interaction effects, we can talk about one. All right, and so this just shows demonstrates what we're talking about there, that the interaction effect is 0, regardless of how we calculate it, whether we take the difference between the simple effects of A or the difference between the simple effects of B, we get the same value. So in this example, we have a situation where the two factors do not interact in terms of their impact or effect on the response. The interaction effect is 0. And this is easy to see if we look at the interaction plot. Remember that the interaction plot is a graphical way of determining whether an interaction exists between two factors when we plot the values of the treatment means. And again, in this example, along with examples 5.2 and 5.1, we are assuming, we're pretending that we know the actual treatment combination means. All right, and so in this ideal or idealistic situation, we can look at the plot and determine whether there is interaction. When we have real data, all right, in a real data situation, we're not going to know the true values of the treatment combination means. We have to estimate those values using data generated by the experiment that has that 2x2 complete factorial treatment structure. Then it becomes more difficult to determine whether interaction exists just by looking at the interaction plot. We can maybe get a sense of whether we think there's interaction by how far from parallel the lines are, but what it really boils down to is in order to make an inference, we have to actually formally test the hypothesis of no interaction. But in this idealistic situation here, we're looking at assumed values of these treatment combination means. And so we see here that the two lines are parallel, and that the fact that they're parallel indicates that there's no interaction between factor A and factor B. We see that the effect, the simple effect of factor B is the same at the first and second levels of A. That vertical distance between the two lines is the same regardless of whether we're looking at A1, level A1, or level A2. Okay, that is why the two lines are parallel. And so that tells us that there's no interaction because the simple effects are equal. And we could make the same argument with regard to the simple effects of A at both levels of B. All right, those simple effects are the same, and so there's no interaction. Now, because there's no interaction, the effects of the two factors are additive. You'll remember that we said that when an interaction exists, that means that the effects of the factors on the response are not additive. But if there's no interaction, that implies that the effects of the factors are in fact additive. And so let's take a look at what that means in the context of this 2x2 complete factorial treatment structure. And so here I've gone back to that first two-way table, and you'll recall, based on our calculations, we have determined that the main effect of factor A is 20, the main effect of factor B is 40, and we've also determined that there's no interaction between the two factors. Now, because of that, their effects ought to be additive. And in fact, that's demonstrated in the cells of this table. So starting off at the cell for treatment combination A1B1, the treatment combination mean is 60. If we go to the over one column to the cell for the treatment combination A1B2, all right, that ought to be 60 plus 40 because the main effective factor B is 40. And that is the case. You'll recall that the mean of the treatment combination A1B2 is 100. Well, that works out. If we go back to the cell for A1B1, and again that treatment combination mean is 60, if we go down now from level A1 to level A2, the main effective factor A is 20, and so if the factors are additive, then the mean for that cell, A2B1, ought to be 60 plus 20. Well, it is, because we know that that treatment mean was 80. And then finally, if we start, let's say, at the A2B1 cell and move over to the right one cell, so that we're looking at the cell for A2B2, then the value for that mean ought to be 60 plus 20 plus 40, because we're now going from level B1 to level B2, and that main effective factor B is 40. And that is indeed the case, because we started off with that, we were told that that treatment combination mean was 120. So that is what it means for factors to be additive in their effect on the response. And factors are additive when and only when there's no interaction between them. If there is an interaction between them, then the two factors are not additive in their effect on the response. Likewise, if the factors are not additive, then we know that there is an interaction between the two factors. All right, so that is the end of example 5.3. In the next lecture video, we're going to move on and talk about some additional things, such as how to proceed in an analysis when interactions exist.